Okay, I'm going to be starting in on the kind of last segment of General Chemistry 2 today. So we've got, for sure, 3 more chapters to do and probably a little bit of a 4th chapter. But the chapters start today with thermodynamics. Next week will be electrochemistry. And then I'm hoping to get a little bit of nuclear chemistry kind of squeezed in. We're a little short on time. I think there were a couple of snow days that have me a little bit behind schedule, but still we'll be covering all of the major topics. So thermodynamics is kind of the most fundamental type of science that you see in general chemistry. And you've seen a touch of it before back in chapter 6. And since I wanted to start getting back from spring break like one step at a time, I'm not going to jump into the deep end today, but mostly spend the time reviewing a little bit of stuff from chapter 6 and giving you a problem to work on before you leave today. I mentioned a couple of weeks ago that at one point you'll be getting a fairly extended extra credit problem where you get to determine what the pH of pure water is at a temperature that's not 25 degrees. So 25 degrees, pH of pure water is 7.00. At any other temperature, it's not too far from that, but it's not 7.00. So by the end of the week, we should have enough covered so that I can give you that as an extra credit problem. So chapter 18, thermodynamics. Thermodynamics is looking at eventually getting to figuring out equilibrium constants. And if you're in physics or engineering, it can be applied to a lot of other things, but in chemistry, mostly it's for chemical reactions. And that eventually is how you'll get to determining pH at different temperatures. Now, there are 3 different functions, primary functions in thermodynamics. One is the enthalpy, and it's the same enthalpy that you saw back in chapter 6, and that I'm going to talk about for most of today's class. The other 2 functions are entropy, which can be really tough to understand if you get too much into the details. It's super easy to understand just in the big picture concept. Entropy is essentially it's disorder, and you can also think about it as unpredictability. So that'll be a big part of the class on Wednesday, and then you can combine the 2 factors to get something called free energy. And I'll be getting to that sometime on Wednesday, and then connecting that to the equilibrium constants on Friday. So this is kind of all of the basics. If you ever wonder why a reaction occurs or doesn't occur, or why it might be mostly products or mostly reactants, it's all based on thermodynamics. So the review is pretty much all I want to get to today. This is back to chapter 6, section 6. And the first thing is just defining enthalpy change. So delta is the same delta, final minus initial. H is the symbol for enthalpy. And it equals the Q is a symbol for amount of heat. And it can be quite a few different units. Typically in chemistry, you'll see it in kilojoules. And then the little subscript here means that this is for a reaction at constant pressure. So any reaction you do kind of in a beaker in the chemistry lab is exposed to the atmosphere, so it has 1 atmosphere of pressure when you're doing the experiment. There are different ways you can do reactions, but in chemistry, that's typically the way most of them are, and so that's why we're working with the enthalpy here rather than different functions. So that's the definition. If delta H is negative, it's called an exothermic reaction. Heat is produced or evolved. So you run the reaction, builds up excess heat, and then distributes that heat to the surroundings. Positive is just the opposite, called endothermic. So you do an endothermic reaction. Initially it gets cold, and then it pulls in heat from the surroundings. So heat is brought in or absorbed by the system. So I've kind of mentioned these terms in passing a few times since whenever you saw it. This was probably back in September or October. But just kind of real basic terminology. Also want to quickly go through, as a reminder, some of the things you can do to calculate enthalpy. So the kind of big thing with thermodynamics in chemistry is you need to, your goal usually is to figure out an equilibrium constant for a chemical reaction. And to get that, you need the free energy, and to get that, you need the enthalpy and the entropy. So for the big picture, you need to figure out what is the enthalpy for a chemical reaction. So I've got 3 different ways to do that, and that's basically what I've got for you for today. So how do you get enthalpies? First one is stoichiometry. So this is worth a quick review. Now, usually I tend to be a little bit relaxed about using the phase labels, so the G for gas there. In the stoichiometry problems, it does make a difference, so I'll be very careful either to say they're all gases or write them out individually. So this is basically just propane, principal component of natural gas. So if you turn on the gas burners up in the lab, this is what you get. Reacts with oxygen and produces carbon dioxide and water vapor. And when you use the burners in the lab, your chemical reaction, the products are carbon dioxide and water vapor, which nobody ever cares about, that you're producing carbon dioxide and water. What everyone cares about is that you're also producing heat, and you get the entropy of this reaction of negative 2044 kilojoules. So negative exothermic, that means it's producing the heat, and this is 2,000 plus kilojoules for every mole of propane. So it's going to be a stoichiometry problem, and you need to do the kind of mole ratio. And a quick reminder with the thermochemistry, the connection is mole to heat, or heat to mole. And here, this is saying that for 1 mole of C3H8, the equivalent in heat is negative 2044 kilojoules. So stoichiometry problem, you have a given amount. On this problem, it's 13.2 kilograms. And the question is, how much heat is produced? So it's pretty much straight stoichiometry. you're going to need a molar mass here. So 1 mole of anything, just add up all of the atomic weights and that in grams. And that is 44.1 grams. And then you can do it step by step, or this one's easy enough. You can just set it out in a straight line, kind of step by step. So you start with the amount given, 13.2 kilograms C3H8. And then you just do unit conversions until you get what you want. So you need to cancel out kilograms, and you want to get it to grams. So you also need to know 1,000 grams equals 1 kilogram. That allows you to take the kilograms here, 1 kilogram and 1,000 grams. So cancel the kilograms, and that you now have units of grams of C3H8. In order to get to kilojoules, you need to be using this, which means you need moles of the C3H8, and you've got that with the molar mass. So 44.1 grams equals 1 mole. And now that you have moles, you can get the kilojoules. So again, whatever the unit is here, you need to put it in the denominator to cancel. So this says 1 mole is equivalent to negative 2044 kilojoules. So in terms of the units, everything cancels except kilojoules from the C3H8. And then 13.2 times 1,000 divided by 44.1, and then times negative 2044 is negative 6.12 times 10 to the 5th. So that's a very big number. This is 61,000 kilojoules, but you have a huge amount of propane in the tank there. And you're also getting a pretty huge amount, so 2,000 kilojoules, that's not 2 kilojoules, 2,000 kilojoules for every mole, so you've got this. In terms of the negative sign, if you just leave it negative sign here, you don't have to think about it. Honestly, the way I do it is ignore the negative sign and just think of it as heat produced. So you can say the amount of heat produced, or you can give it the negative sign. Either way amounts to the same thing. So that's a kind of stoichiometry review. Next comes a Hess's law review. And you were actually doing problems a lot like Hess's law recently. So this one shouldn't be completely out of nowhere. And kind of just a reminder, the point of this review right now is that in order to get the equilibrium constants, you're going to have to figure out how to get an enthalpy change and an entropy change. So this is step one. It's also a good review for anybody who's taking a test involving chemistry sometime in the future. Stoichiometry definitely will be there, and Hess's law almost for sure as well. So here is the problem, 3H2. This is practice problem 6.9. 3H2 plus O3 forming 3H2O. So you're looking for enthalpy change for the reaction of hydrogen gas, which is the normal state for hydrogen, and ozone, producing water vapor. And you're given two component reactions. 2H2 plus O2, 2H2O gas. And that's negative 483.6 kilojoules. And the second one you're given is 3O2 combines to form 2O3. And for this one, it is positive 285.4. Okay, so just a quick reminder, what you're doing is trying to take these, figure out what combination will give you the overall reaction. So if you, say, double one of these, you have to double the delta H for the reaction. Half of it would be half of that. And if you reverse the reaction to, say, make it 2H2O producing this, then you reverse the sign, so the negative would become a positive. So what you're looking for is just kind of going from left to right in the equation you're trying to get is 3H2 on the left-hand side. So you've got 2 here. It's on the left where you want it, but to convert 2 to 3, you have to multiply by 3/2. So you do that for the whole equation, and you get 3H2, and remember, you have to now multiply everything by 3/2. So 3/2 is O2 and 3H2O. And whatever you do to the equation, you also do to the delta H. So 3/2 times the negative 483.6 is negative 725.4. Okay, so then back to what you're looking for here. The next one is the O3, 1 mole of it on the left-hand side. So you look for O3 in your component equations. 2 problems. You have twice as much as you want, and it's on the wrong side. So you have to reverse it and multiply it by 1/2. Okay, so reversing it makes the ozone on the left-hand side. Half of it means you've got O3. And then on the reversed right-hand side, half of 3 is 3/2 O2. Okay, so this one was reverse and half. So you reverse the sign, it'll be negative, and half of this value is negative 142.7. Okay, so going to combine these two. Now this step is really just to check to make sure you have the right thing. The question is, what is the value of delta H? So if you take a look at this, you've got 3/2 O2 on the left of the arrow, 3/2 O2 on the right of the other arrow. So those are going to cancel, and you've got left over 3H2 plus O3 on the left-hand side, and 3H2O on the right-hand side. So that is what you're looking for. So that's not really part of the answer. It's just to check that you have the right combination. So when you combine these two, negative 868.1, then you have confidence that you do have the right answer. Okay, so all of that's been reviewed, and the next thing I've got is also from Chapter 6, but it's the piece from chapter 6 that I left out at the time because we're coming back to it now. And this is something that is, well, basically all computerized these days, but also based on the same concepts. That you can get the kind of standard enthalpies of a lot of standard reactions. These are standard enthalpy of formation. So standard temperature and pressure, which means 25 degrees Celsius, 1 atmosphere pressure. And that's basically, if you go in the lab, you're going to be pretty close to that almost no matter where you are or when you're doing it. So the F is for formation of the compound from elements in their standard state. Now, this one is a little bit tricky. You have to kind of know some stuff. The first part is easy. You have to know if I give you something or if you see it on a test, is it an element or not? And you'll have a periodic table, so if you see SC, you look it up. If you see an SC up there, you don't even have to know what it is, but you know it's an element. Now, the tricky thing is to recognize, say you're looking at oxygen. There are 3 types of oxygen that you're likely to run into. Oxygen atoms, oxygen O2 molecules, and ozone. So which one is oxygen in its standard state? They're all pure elements, and there's no way to figure it out. You just have to know this part. So standard state of oxygen is O2. Now, there are only 2 types, well, and a couple of odd ones, but only 2 types that I remember after doing this practically all my life. First one is H2, and then the kind of gases, N2, O2, F2, O2. All of the group 7 elements are diatomic molecules. And the gases, hydrogen, nitrogen, and oxygen, are diatomic molecules. So, not really sure how to make this easier than group 7, you can just kind of remember. And by now you've seen enough of these that you've always seen whenever it's been chlorine, it's been Cl2. So anything in group 7 is always a diatomic molecule. And then you're kind of left with just 3 important ones here. Hydrogen, nitrogen, and oxygen, always diatomic molecules. So just remember that. And then the kind of weird one is carbon. There are 2 states of carbon that have been known for a long time, and then there are some relatively modern ones that are also not standard state. The 2 that are usually listed in tables that you'll be seeing are diamond and graphite.